So the subject for today, for the first session, is topographic bias. What does that mean? We always discuss that if we have a point there outside the Earth, and there's the topographic masses here, and here is a geoid, for example, and if I want to use the solution of boundary value problem, I have to do two things. First, I have to remove the effect of topographic masses. First step is to remove the topographic mass effect. And the second is downward continuation. So this means like that. I clear this, then I have no topographic space. Thereafter, I continue this downward to the geoid. But now, assume that I do not remove the topographic effect and continue the data down to the geoid. Well, we are violating the theory. We are violating the theory because we always assume that there should not be any mass outside it, but we do not care about it. And we just continue this downward to the geoid. What will happen? What we get actually here will contain a bias. In fact, you are not coming to the geoid directly, you come to another surface. And for example, if you have continued downward the gravity anomaly here, the gravity anomaly down, this gravity anomaly is biased by topographic mass. So it is not exactly what we want, because the effect of topography was ignored. And what will happen if we use this gravity data to compute the geoid model? The geoid will be biased. So if, for example, do we have this in reality? Yes, of course. When you have the gravity models, and when you compute this gravity data, and use this gravity for computing a geoid model, you need to continue them downward to the surface of the reference ellipsoid. But you have not removed the effect of topography. Let me explain it with a figure to understand, so that you understand the concept easier. And we know that nowadays satellite gravimetry is a hot subject, and we have the Earth, and we have satellites moving around the Earth, let's say like that, and they are perturbed around the Earth, and these perturbations or second order derivatives are computed, and a reference ellipsoid is considered, or as it R, for example, with R and E2, and the data are continued downward to this R. If you open the gravity model, you will see a GMR there. This means that this R is actually the semi-major axis of the reference ellipsoid. It means that they all continue down to the surface of this sphere. Yes, but they have gone through the topographic masses. It means that the topographic effect has not been removed from satellite data. They just use satellite data for computing the spherical harmonics. They do not have any attention to the topographic and atmospheric masses. So it means that the geoid that you compute from this gravity model, they are already biased by this topographic and atmospheric masses. This is why that we have to correct them when we compute the geoid model. So this is the reason that we are going to discuss about topographic bias today. So the question is, how can we do so? What is happening here? Now assume that I have the topographic masses here and I have the data. Let's consider the potential, which is easier to discuss with. And it goes down to the geoid. Goes down to the geoid. And what is happening in reality? So if I remove the effect of topography, let me write effect of topography. What I get down here will be the effect of topography continued downward here. Downward here. And the next step is to restore the topographic effect by the internal side. So this means that this gravity that I have here, this one, which is continued downward, I will write this V minus V external minus V topographic effect continues downward minus, if it is a bias we should remove from the data, and then after restore it, it will be VI VI plus CV V inside. So if we assume that this potential is equal to this one, the downward continued one, the potential which is continued downward is here, and the same with the potential of I. Therefore, what remains is topographic effect continued downward, should be minus the internal effect. This is topographic bias. So we can compute this topographic bias and remove it from the computed geoid. How do we do that? So simply, if you remember, the potential of the topography was summation from 0 up to infinity, R over R n plus 1, summation minus n V and M external Y and M theta and lambda. So what how can I do the downward continuation of this topography? How? That's simple. If you assume that R is equal to this R. It means that you are doing a downward continuation. Therefore, simply you can write m minus n, v and m, y and m, theta and lambda. Now we look at the I, internal one. Very similar formula. If you remember, it was R over R, n, m minus n, y and m, I, y and m. And I want this one to be at the surface of the sphere as well. Therefore, R should be equal to R. In this case, Vi at R equals to R will be summation 0 up to infinity, summation m minus 1, Vn, mi, y and m, theta and lambda. Good. We have an equation here. We have another one here. And it is enough that we subtract them from each other. So, if I subtract them, for example, if I write topographic bias minus this plus Vi will be summation from 0 up to infinity, it will be R over R. Summation minus n to n, V and m external minus n plus V and m internal. Theta and lambda. Now we work on this term. If you remember, y external was that 4PGR2, if I'm not mistaken, please correct me if I'm doing wrong, and rho topography, it will be H and M over R plus n plus 2 over 2R2 H and M2. So, and V and M internal, we have had similar thing here. 2m plus 1. It was J and M R again. It was minus n minus 2, and if I'm not mistaken, 2R2 H and M2. But I have considered here only one term. It's only to second term. So now I subtract them from each other. If I do so, I come the external and M downward continued minus minus V and MI R over I. Okay. This one will be this one, and this one will be minus this will be 2n. Let me see, 4PG R2 rho over 2n plus 1. It will be 1 over 2 over R2 minus n minus 2 minus n plus 2 and H2nm. So as we see, 2n by 2n, you see, maybe 2n. I think it was minus plus 1, I think. It was a mistake, I think I wrote here. It was not 2. Then it will be minus n minus 1, which can be written. This can be simplified by that. Therefore, it will be 4 pi g. We have R2 here. This R2 is simplified by this 2 into 2 by 2. Therefore, I can write 2 pi. Two pi d rho t, and what is remain is H2 and m. Now, if I insert this back to the spherical harmonic expression, downward continuation plus internal type R over R is summation, and from 0 up to infinity, m minus n up to n, 2 pi g rho H2 and n y and m theta lambda. That's all. We are almost there. So this 2 pi, this 2 pi g is constant. It goes outside. I will write 2 pi g rho summation H2 and m y and m theta lambda. Okay, what is this then? This is a spherical harmonic expansion of H2. That's all. Therefore, I can write topographic bias equals 2 pi g rho H2. That's simple. However, this is only because we use the Taylor expansion for the binomial term of modeling the spherical harmonic up to the second term. If I continue do that harmonic expansion up to the third term, I will obtain another formula. Let me write this spherical harmonic expansion for them, then we can see. For example, if I have had the spherical harmonic expansion of external type 4 pi g r2 rho 2m plus 1. It was m r plus 2 over 2r2 and m plus m plus 2 n plus 3 6r3, and it will be h3 and m. And for the internal type, it was similar if I consider higher term for the binomial expansion. The first term is the same. The second one was n minus 1, 2r2, that's 2, and m, and I remember it should be 6r3 n minus 1, that's 3. So if you use this one, I'm not sure about this signs. If you use this formula, then you will come to a more complete formula for topographic bias that I write it for you directly here, and you can follow the mathematical derivations yourself to find it. Of course, I have written this in my book too. It will be, if I could do that, it will be this term plus third term. That's it. Oh, it should be plus. So if you consider up to the third term of this expansion, of course, this term, then you will come to this formula. That's all. So what is this? What should you do with that? Simply, we keep the formula in mind and I clean everything. When you compute a geoid model, for example, from a gravity model, and it should start from 2 up to infinity, r over r and plus 1, it should be 1 over gamma here as well, minus n till n, 2 t and m, y and m, theta and lambda. You have computed a geoid model. What you should consider for geoid modeling using spherical harmonic is that this r is actually the semi-major axis of the reference ellipsoid. This is this one. But what you need to have is the geoid at the surface of this ellipsoid here. Therefore, you need to do two things. First, convert geocentric latitude to geodetic latitude, and second is to compute geocentric distance to surface of ellipsoid. It means here, this distance you can compute it based on this angle. So this distance you need to consider, and also after changing this geodetic latitude, You will use this term, but when R is a little bit larger than R, then you have the downward continuation. And don't worry, up to degree 2000, it is convergent. You will have no problem to do this. Then you will compute a geoid model at the surface of the ellipsoid. But you have not considered the topography effect. So simply you compute the topographic effect, topographic bias, which is this formula, bias is 2 pi g R2, not R2, R2 is 2 pi g rho t h and m. H, not an m anymore. H2 plus H3 over 3R. Compute this term and remove this from the computed geoid to have your topographic effect. To remove the effect of ignored topography in the gravity models. This is what you need to do in your project. For the atmospheric bias, we will do the same. So now, atmospheric effect. Atmospheric bias. The same thing, the same issue, but here we have atmosphere. Here we have atmosphere. And the points, they are up here. If we ignore atmosphere and perform the downward continuation, then both, and we come to, for example, delta G star here, it will be biased for atmosphere and topography. Both. This means that we have to correct, we have to remove both biases. So I simply write the result for the atmospheric bias, and if you compute the spherical harmonics of the external type for the data and internal type, and come to the potential bias of atmosphere, you will have this spherical harmonic expansion for that. And it will be based on the power model that we have discussed for PG R2 divided by 1 over 3 minus V. To rho. These two should be inside. And if I want to write it in a simpler form, I can write like this, not in terms of spherical harmonics. So spherical harmonics are here. Yn. The simpler form it will be for this bias, atmospheric bias will be 4 pi g r2 3 minus v zl2 minus v r plus minus 4pg h2 divided by 2 plus v minus 2 h3 divided by 3r. Very similar to the topographic effect, especially this term, except this term, this coefficient, and this one is the effect of the potential effect of this term. If we have a topographic effect, atmospheric effect, the effect of atmosphere disregarding the topography, and later the effect of topography is computed and removed from that. That's the principle. That's the atmospheric bias that we can compute and apply it to the geoid computer from the gravity model to correct it. So I go and